considering I did all of my studies at TU Munich. It's also nice to see some familiar faces. So thanks for the invitation to be here today. And I'm going to talk about stuff I actually got interested in my last year of my PhD. So I thought it was a fitting topic, which are quantum algorithms for semi-definite programs. So we heard some advances in hardware. Now I'm going to try to talk about some ideas on what to use quantum computers for. And yeah, so this is going to be a talk about quadratic unconstrained binary optimization problems, QUBOs. So we are given some matrix C, symmetric, and we want to just optimize that function over there. And you know, you can encode many NP-hard problems into this. It's a widely studied problem with thousands of applications, so you can see this as finding the max cut of a graph, or if you're coming from physics, solving this sort of problem is the same as finding the ground state of an Ising model up to a sign change there. So appears everywhere, and also in quantum computing, people have proposed various algorithmic frameworks to potentially obtain quantum speedups to solve these kinds of problems. For instance, you can think of quantum annealing or classical annealing, also QAOA, and so on. So these things are studied to death. But they're very hard in general. So we don't really expect to be able to find efficiently the solution to these problems. So people have tried to look at relaxations. And one of the standard relaxations, and in some sense it's the best thing you can do, is this Goemans and Williamson SDP relaxation, SDP being a semi-definite program. So instead of solving that original problem I showed you before, you solve this problem, so you maximize this scalar product there is just the Hilbert-Schmidt one, so trace C and Y. So you optimize over all matrices that are positive semi-definite with diagonal 1. And you can solve this problem in polynomial time in the dimension, and you can actually show that the solution to that problem gives you an upper bound on the value of that QUBO you started from. How do you see that? Well, you can actually rewrite the QUBO exactly in the same way as that program I wrote in the previous slide, but you also add a rank constraint. So you now do not optimize over positive semi-definite matrices, but also rank 1 once. Then you can see it sort of, the matrix factorizes into, because of the diagonal constraint, into a vector of plus minus 1 entries. So you sort of recover the original QUBO problem. We don't really like the rank equals 1 constraint, so we drop it. We just ignore it, and then we get a convex problem, and that one we can solve in polynomial time. We are happy with. So this is the sort of idea that Goemans and Williamson came up with in the 90s to get an upper bound. But what really made this interesting is that you can also then get a lower bound to the problem and also a feasible point to this QUBO by doing what they call the randomized rounding routine. So what you actually do is you do some sort of Cholesky decomposition of the feasible a point you found, or your solution. So you take the square root, and then you multiply it with some Gaussian vector, and then you just look at the signs, and then you look, depending on the sign, you say plus or minus 1. So you get some sort of feasible point of the original QUBO. At first, it might seem a bit arbitrary, but you can actually show that this performs reasonably well. So for instance, if you are looking at the max cut instance, this is guaranteed to be 0.87 from the optimal. So from this solution, you get both an upper and a lower bound, and this you can do in polynomial time, and under some complexity theoretic assumptions, this is in principle the best you can hope for in polynomial time. And so this is a very nice result and a very nice framework to handle large instances of these QUBOs. However, in practice, these algorithms, they are constrained by memory. So if you start running these things on your laptop, you suddenly see that when you start looking at thousands or maybe tens of thousands of points for your QUBO, the dimension, you start running out of memory. This is one of the main issues. And people have then proposed some sketching-based methods that can then handle up to 10 to the 7 for sparse entries, but solving SDPs at large scales is a big problem. Now, people then have also looked at quantum algorithms to try to solve these SDPs. I have done that, for instance, in the past, but there was then some, and admittedly, the quantum speedups we found were small, so even smaller than what you usually get with like a Grover speedup, so not even a quadratic speedup. And as usually is the case with quantum algorithms, the constants aren't that great. And then there was some recent friendly fire from my collaborators who showed that our previous algorithm is actually a so-called galactic algorithm. So what is a galactic algorithm? It's one where the constant in the big O are so bad that you have to look at instances the size of a galaxy to actually have a speedup, right? So, and they showed it's indeed one of those. But I want to show that if you look at more specialized instances, then we can actually get huge speedups using our previous methods. So our previous methods were based on the so-called matrix multiplicative weight framework to solve SDPs. And I'm not going to go through the details of how it works, but just going to give you the gist of it. And essentially, this algorithmic framework reduces solving an SDP to preparing quantum Gibbs states and estimating expectation values of those quantum Gibbs states. It is an iterative algorithm, and the number of iterations it requires is logarithmic in the dimension, which is great, but polynomial in the precision, which is kind of bad. So what you need, the take-home message is somehow that this framework allows you to take your SDP and then reduce it to preparing some sort of sequence of Gibbs states. And you don't have to do that many when it comes to the dimension, but you kind of have to do many in terms of the precision. And well, you could then think, oh, Gibbs states, maybe quantum computers could be a good way of preparing quantum Gibbs states. However, there are some bottlenecks to then use this matrix multiplicative weight method to get exponential speedups to actually solve interesting SDPs. One of them is that for some generic Gibbs state, we don't really expect a quantum computer to be exponentially better. We just expect at best a quadratic speedup, because we're not really talking about quantum many-body Gibbs states. We're just really talking about e to the minus some big matrix. And then if you don't have more physical structure, I at least don't see why immediately why you would expect huge quantum speedups. But if you have a more physically motivated Gibbs state, then I think the story could be different and is different, as I'll argue. Also, the number of constraints we have in the SDP is linear in the dimension. So how do you check for linearly many constraints in a very efficient way? That could also be a bottleneck to actually get exponential speedups. And, well, you could even say that writing down some sort of solution to your SDP, or maybe to the original QUBO problem, will also take time that is at least linear in the dimension. So how could you expect to do that very fast? And last but not least, as I said, this method has a very poor scaling in precision. So as long as you need a precision that scales with the dimension, you're cooked, right? So you need to look at problems where a very rough answer is sufficient for your application. And I'm gonna argue that there are some instances of SDPs where all these things are fulfilled, where we overcome all barriers. I put a bad check mark on, or wrong check mark on the precision overhead, not because it's still an issue, but also because, let's say, we haven't come around the fact that the convergence in precision is bad, but for our purposes, it will be okay. And just to, and so we found instances where we can solve these STPs exponentially faster than with current methods, and also do the rounding, and all of this based on ideas coming from quantum many-body. So just to show you one instance here, here is an STP we solved using our methods, where we were able to solve up to dimension 2 to the 50. When my colleague did the numerics, he was looking at the min version of the QUBO, so that's why the plot might look weird at first. But sort of the blue line there with the dots is the lower bound we obtained by solving the STP, and the red one, the points we get with the rounding. And you see that we actually compare to various other heuristic and rigorous methods to solve these STPs, and they stop at many orders of magnitude before what we can do. So we are very happy about these results, but you should also be a bit skeptical about this, right? Because this might also be a bit too good to be true. So there's some caveats about the instances we can solve. To the best of our knowledge, this is the largest STP people have solved, but there are lots of our instances are highly structured, all right? Okay, so what are the steps we take to make sure that we can actually get huge speedups using quantum or quantum-inspired ideas to solve these STPs? The first is to assume that the matrix that describes your QUBO is sparse in the Pauli basis, in the sense that you can expand it as a linear combination of a few Paulis. And one way of quantifying this is just expanding it. Oh, and from now on, I'm always going to assume that we're looking at instances of size 2 to the n for large n and the number of qubits. And one way of quantifying this is that when you expand the matrix in the Pauli basis, it has a small L1 norm, that vector. You can make this connection between sparsity and this norm rigorous using like some matrix Chernoff bounds. But for simplicity, let's just assume for now that indeed we only have a polynomial in n, many of these coefficients that are different than 0. Another simplification I'm going to do for this talk that we don't necessarily do in the paper is to also assume that all of the matrix polystrings that appear in this decomposition act on at most k qubits, okay? So, and k a constant. So in some sense, if this matrix C admits such a decomposition, it looks precisely like a quantum many-body Hamiltonian, right? Acting on that, like that is k local. And when you have such a QUBO matrix, then you can actually exploit this physical structure you have to design better ways of preparing the Gibbs states that are required for these SDP solvers. Now, what are these graphs? One example are, you can show that they are so-called, or what graphs do these matrices correspond to? So they are subgraphs of the so-called Hamming-Ball graphs. So these are graphs where you essentially connect to, the vertices are given by bit strings, and two bit strings are connected if they are Hamming distance at most k from each other. And these are the sort of graphs that can be expressed in this way. And maybe they arise naturally in coding theory, so maybe these instances have some applications there, but I haven't found one yet. But again, in the paper we also look at other instances. This is just a simplified setting where it's easier to visualize what's going on. Now, okay, so this way we are making this assumption on the matrices we're going to target already allows us to hope for better quantum algorithms to solve these instances. But we still need to deal with the fact that we have exponentially many constraints for general QUBO problems, which is going to be one of the bottlenecks when implementing them. So one thing one could also note is that having this constraint that all the diagonals of the matrix are the same, 1, in our SDP, can be rewritten as just demanding that the expectation values of all Pauli Z strings are 0. This is equivalent, right? So like you being maximally mixed on the diagonal and the computational basis is the same as all Pauli Z strings having expectation value 0. Now, this gives us a very natural further relaxation of these SDPs. Instead of demanding that all the Pauli Z strings have expectation value 0, we just say that a few of them, which we're going to choose in a judicious manner, should be small. So, and hopefully, this way, we can then reduce the number of constraints, maintain a more physically motivated structure for our SDP, and then and solve it much faster. So we look at this further relaxation of Goemans and Williamson, where we just impose some subsets of qubits and say that the Pauli Z strings on those qubits should have expectation value 0. And if you just say like, oh, I'm just not going to impose any of these Pauli Z constraints, then you just get back sort of what people call the spectral bound. So this will just be like computing the eigenvalue, largest eigenvalue of this matrix C. And of course, if you pick all Pauli strings, this is the same as the usual Goemans-Williamson. So it's some sort of like hierarchy of problems. Okay, and well, how do we then find good subsets of Pauli strings to impose our constraints? It turns out that one thing you can do that works out is you can look at the group that these Pauli strings that appear in the expansion of the matrix generate. So you just take all the Paulis in this expansion. We assume they're only poly and many, so you can look at the group they generate. And you can look at the intersection of that group with diagonal Pauli, so Pauli Z's. And it turns out, and then you can look at that algebra. All of this you can compute efficiently. So if I give you these Pauli strings, you can do some, like you can use the like Z2 representation of those guys and compute this diagonal group efficiently given the Paulis. And it might not be too surprising, but it turns out that if you just solve the SDP not with the whole diagonal group, like all the Paulis, but the Paulis that are in the group generated by those in the expansion in C, that you can recover the original value of your SDP. On top of that, I mentioned before that you have to be careful with these problems, with the scaling and precision. And it turns out that also here, the problem is very stable. So the precision with which you need to solve this SDP to recover a good solution only scales with the size of this diagonal group. So as long as this thing is small, so let's say you have like polynomial in the number of qubits, then the scaling and precision will not bite you. And you'll still be able to get very good solutions with only a very rough precision. And the sort of Gibbs states you need to prepare to solve the SDP will be of the form below. So you'll have to have one component which is in the direction of your cost matrix, which we assume to be some sort of many-body Hamiltonian, right? And the Pauli Z strings in this diagonal group. And what do we, you might ask, well, what is the temperature? And we don't have exactly we have some sort of average temperature we can bound. So the L1 norm of all those coefficients will be roughly n over epsilon. So you could say in some sense that the average temperature is epsilon. And yeah, so these are exactly the problems we need to solve for SDP. Sorry, the Gibbs states. And some of you might be thinking, oh, well, maybe if this diagonal group is very small, then the problem becomes easy or becomes trivial. I would say that even if you, in the simplest case, where this diagonal group is just plus minus 1, recall that this is actually the same as finding more or less approximating the ground state of a quantum many-body Hamiltonian. So even for small diagonal groups, solving this is not necessarily easy, right? Or as hard as it gets, I guess. Yeah, so this, and how, maybe I can give you a proof sketch. And the idea is essentially that because we have this iterative solver that works by preparing a sequence of Gibbs states, we get all the constraints which are not in this algebra generated by the Pauli strings for free. So they are, you never violate these constraints as you keep taking exponentials of C plus these other Pauli strings. So that's why we never have to actually look at them. So these constraints are in some way redundant. And then to get the precision bound, we actually use some previous bounds we showed for this problem, showing that if you have a good total variation distance of your diagonal to the maximally mixed state, then you can approximate a good solution to the original SDP. So we show that indeed in this case you have such a good total variation bound. All right, so what is the sort of recipe to get an exponential speedups? What are the instances for which we get exponential speedups? In principle, you need to be able to you need to have a small diagonal algebra. So for that 2 to the 50 SDP I showed you, we looked at a variation of a 1D cluster state as our Hamiltonian, and cooked it in a way that this diagonal algebra had, like, I think, size 16 or something like this. But that was already sufficient for us to see something, and something better than just the spectral bound as well. And if you can then prepare such Gibbs states efficiently on your quantum computer or classical computer, for instance, in our case, we used tensor network methods, then you get an exponential speedup compared to classical solvers. So again, for instance, if you have commuting 1D Hamiltonians, then you can use tensor network methods to get an exponential classical speedups, like I showed you in the plot. And if you can prepare these Gibbs states on your quantum computer, then, for instance, we expect also, we know for certain 1D systems this will also be the case. Then we again get an exponential advantage over classical solvers on quantum devices. Now, maybe I should also tell you that we are also able to do some sort of Monte Carlo, 2 minutes, right? Yeah. So a way of estimating the energy of when we do this randomized rounding I mentioned before, because maybe you're not interested in the actual solution, but I'll maybe skip this in the interest of time. And yeah, I just want to say that we still don't have a way of doing this randomized rounding on a quantum computer. This is something I'm very interested in doing. And we are also looking at some more, let's say, practically relevant cases where we expect large speedups and are able to get large speedups already for some classical simulations. These are so-called Kronecker product graphs, which appear in network theory. And there we already do classical simulations for like 24 qubits, which was beating state of the art. Another very natural question is, can we do similar tricks for other SDPs people care about in practice? And I mentioned this diagonal algebra approach to reducing the number of constraints, but this leads you to only having like analytical bounds for very special families. We also have some heuristic ways of reducing the constraints that perform well in practice, and it would be nice to also get analytical results for that. And yeah, so with that, thank you for your attention, and I'd be happy to take a few questions.
Thank you, Daniel, for this very interesting talk. Are there questions? All right, let me try. Oh. See, that's what happens if you don't pay attention.
Yeah, so you're imposing a lot of structure on the problem by making all of these different assumptions. So how do you know that the problem also doesn't just get much easier classically? Do you have any sort of evidence for this?
Right, so that's, I mean, I guess it depends what you mean by much easier classically. Do you mean the original QUBO or the SDP or?
Well, I mean, the SDP with all of these constraints, right? You're somehow claiming you have some exponential speed up there.
It gets much easier classically because we just found an algorithm that does it much easier classically, right? But maybe I'm not aware of other methods that will lead you to like solving them at this scale. But I agree with you. I've asked a few people. Nobody was able to point something out to me. But I completely share your concern, say that it would be nice to have some argument as to, for instance, whether these instances are still NP-complete and things like that. I agree with you that this is something we're missing.
Any more questions? Yes.
Yeah, very briefly, if you have a quantum algorithm yielding some speed up, it would be nice to know what kind of hardware requirement you have for implementing such kind of algorithm. Give you a hint on that? Sure.
So I guess, let's say what we need are ways of preparing these thermal states at some finite temperature. So there are now many different proposals of how to prepare these thermal states. I think it will already be interesting in the regime of, let's say, 25, 30 qubits. You could maybe do something interesting there. And then because you want to do some sort of engineered dissipation, probably you're also going to need some auxiliary qubits for that. So I think that that's sort of the regime where I think maybe already something interesting could be made.
Okay, so maybe in the interest of time, I also have other questions, but maybe we can sort out these things over lunch. Yes. So let us thank Daniel again for this very nice talk.